So we talked about bar magnets and permanent magnets and things. We got to finally circle around to electromagnets. And there's this thing called Oersted's discovery. And first, I want to like fill in some blanks here, and then we'll talk about Oersted. The right hand rule. Right hand rule is a pattern of of magnetic fields for memorization. So it's a memory strategy. Oh, I didn't make this line long enough. A memory strategy for ooh, for magnetic field form generated by flowing electric current. Maybe I should say formed. Oh man, I got to work on these blanks. Anyway, flowing electric current. I don't know if I probably could have just written that out without it being a fill in the blanks. Would have been the same amount of time. Um, and when we're talking about flowing electric current, the variable we use is I. Hopefully, you've seen that before in an earlier grade. Probably you talked about Ohm's law, V equals IR, or something like that. The units that we use are amperes. Now, again, that's somebody's last name. Oh, look, even an accent aigu. But nobody, well, not a lot of people say amperes every time they talk about current. Most people will talk about amps. And again, we're just shortening somebody's last name. Disrespect, but still, okay? Or maybe so much respect. I mean, hey, if somebody likes you so much that they shorten your last name, maybe that's like next level. Anyway, we shorten it even more just to one letter, capital A. Now, one of the things that I like to talk about when I teach grade 9, but I'll make sure that we hit it here. When we talk about current flow, there's conventional current flow. Conventional current equals flow of positive charges. Ooh. Oops. Flow of positive charge. Now, of course, that's a lie. Positive charges aren't mobile. It's negative charges that are mobile. But there were all these rules that got set up around the turn of the last century where we were talking about the flow of electrical current, and people just chose this direction as the flow. Remember, around the turn of the last century, we were just discovering the electron. So we weren't quite sure about what was happening, and yet a whole bunch of textbooks got written because people were excited and they were learning new things. So we have this thing called conventional current flow, which flows from the positive terminal of a battery to the negative terminal. So, hey, we could put a positive terminal on a power source and a negative terminal up here. The current flows from positive to negative. No problem with that, except that it's physically wrong. All that means is that there's this thing called conventional current flow, and then there's the opposite, which is electron flow. And electron flow would flow from negative to positive. Anyway, all the right-hand rules that we talk about are based on conventional current flow. And we can blame history for that, okay? The royal scientists or something like that, all right? But so we're not going to pin it on anybody in particular. But when the current flow does flow from positive to negative, this thing called the right-hand rule, well, there's a story associated with it, and it's called Oersted's discovery. Really, what happened was he was teaching a lesson, and you can watch videos on people telling this story better than me. But he was teaching a lesson to a group of university students. University students were watching him. He was talking about fundamental forces, charges, all that sort of stuff, and he's teaching about how magnetic fields and electric fields don't interact with each other. They're not the same thing. They're from different sources. And he has a physical setup on his desk. You can imagine maybe the physical setup looks something like this, where there's an electrical wire running along the surface of his desk, suspended above the desk. And he places a compass down on the table because he had just been talking about magnetic fields and now he's talking about electricity, but he puts a compass down underneath the table. And lo and behold, that compass points in a direction that's perpendicular to the wire. And somebody in the front row of the class says, "Sir, why is it pointing perpendicular to the wire? Is that a thing we should notice?" I mean, that's not pointing north anymore. North is over that direction. It's not perpendicular to the wire. Fair enough. This intrigues the man. So in the middle of the lecture, they disrupt things. He says, well, how about we take the wire and we kind of we rotate it so that it goes in a different direction. And then we'll put the compass underneath of it again. And again, the compass ended up orienting itself perpendicular to the wire. She's like, oh, this is an interesting thing. So then we take that same wire. How about we run it vertically? And it turns out that if you take a compass and you place that compass anywhere in a circle around that wire, the compass needle will trace out a circle. And at all points, it's perpendicular to the wire. And people are like, wow, this is a neat thing. And so this is why it's called Oersted's discovery. Really, it should get a little bit of credit should go to the kid in the front row, right? But we never know that person's name. Oersted's discovery says that if I take my thumb and I point it in the direction of the current flow, then my fingers will wrap, my right hand fingers will wrap in the direction of the magnetic field. So grab your hand. You got your hand in your hand? Take your hand, and here, I'll zoom out so that I can illustrate a little bit better. Take your hand, thumb in the direction of the illustration. If you like, let your pen or pencil be your wire and let it flow from from positive to negative. So that's the direction of current flow. And wrap your hand around it with your thumb in the direction of the flow. And your fingers are going to wrap in the same orientation as the magnetic field orientation around that wire as the current flows. You actually get a circular wrap of electric field around, or magnetic field around that wire. And here we got an illustration. I'll zoom in a little bit closer. This is the illustration of the idea that, hey, if we run a piece of wire through a piece of paper, we could slide the piece of paper up and down the wire with compasses mounted on the piece of paper, and those compasses would trace out that circle. That would be like next level if we were going to try and demo this thing. Am I kind of selling the physicality of what's going on? Make sense to people? I remember there used to be a Science Center demo like this before they got defunded, where you could play around with this thing. And it really works exactly as I'm saying. I just don't have the physical setup for it. Anyway, one way that people tend to illustrate this, because I feel like these textbook ones are hard for us to reproduce by hand. Some of us aren't artists. I had this teacher one time. He was really into the idea of the toilet paper roll. Here's my toilet paper roll model for a wire. I got my toilet paper roll. I can make it kind of three-dimensional. My toilet paper roll. And the current is flowing out of the toilet paper roll. If the current flows out of the toilet paper roll, I should be able to talk about what's happening with my right hand. Here, look, my hand is pointing to the left, to the right. My thumb is oriented in the same direction as the current. Notice that my fingers are wrapping down in the foreground. Fingers are wrapping down in the foreground. And so this toilet paper roll model is a nice, quick, easy illustration for how to figure out the magnetic field orientation in the foreground, and also recognize what direction would the magnetic field be going in the background behind the toilet paper roll. And they're going to go up, right? So we got to be able to think three-dimensionally. We don't have to think three-dimensionally very often in this course, and so this is sort of some of the training on that, okay? Another thing is, what if we think about the current traveling into the page away from us? So this is a wire. This X here represents a wire, and that wire has current traveling away from us. So I think I'm going to add into my fill in the blanks. When viewing a cross section of a current carrying wire, a dot represents current flowing towards you. While an X represents current flowing away from you. So this is another way to illustrate vectors. This is current flowing into the page away from me. That's a vector of current flow away from me. This is a vector of current flow coming towards me. And people say, why did they use X's and dots? Look, I think what makes sense, you ever see like There was a summer where I was an archery instructor at a camp. But can you imagine old-fashioned arrow? If an arrow flies at your face, what's the thing you're going to see? The point. If the arrow flies away from you, aren't you going to see the tail feathers? So whether or not that's really why they chose that, that's what I always picture. I always picture literal arrows from archery flying at my face. Why not, right? It's an arrow. Why not be literal about it? Anyway, the right... Oh, there's a typo. The right hand. Right hand rule for straight conductors still applies even when it flies away from you and flies towards you. Take your right hand. Confirm. Point your thumb into the page. Like actually point that thumb into the page. Confirm that, yeah, if it's pointing away from you, the magnetic field would orient clockwise. When it's going towards you, do your fingers wrap counterclockwise? Answer is yes, right? So it still works. And we want to be able to check our diagrams with your right hand. Now, the reason I'm actually filling in a blank that's right hand is because it has to be your right hand. Can't be your left hand. And so if you're somebody who gets your right hand and your left hand mixed up, this really matters. If you get really stuck, face your palm away from you. Your left hand makes an L. Okay? Don't get mixed up there, because if your palm's towards you, it'll also be an L when your right hand is present. So make sure that you make your palm away from you, have it firmly placed on your desk, L. If you're like me, I always think about my lower hand on the hockey stick being my right hand. Then I have some people say, well, wait a minute, I just remember my right hand because I write with that hand. Right, spelling. Anyway, W-R-I-T. If you're left-handed, that doesn't help. Anyway, that's all I got to say about that. Now, you can always tell people that are doing the electromag exam in engineering. They're in a great big hockey arena. They got all the chairs all lined up, and they usually separate it out. One row of desks is like the physics exam. The next row of desks is psychology, because they like to have their P's next to each other, right? But they always alternate desks so you're not cheating off the person next to you. And you can tell the philosophy people because they're always scratching their head and pondering things. And you can always tell the engineering people because they're grasping at invisible wires with their right hands, trying to figure out the orientation of the magnetic field. And for real, I watched an EM exam one time, and I could tell the EM exam when I was proctoring. EM exam, all these people doing the electromag exam, and they're all like grasping at the air, trying to find the magnetic fields and figure out the orientation. Honestly, they look like a bunch of people that got hit in the head or something. But it was, they're clever people. They're clever people. But this is an electromagnetism exam. They must be. Anyway.